Let's continue with our Bootcamp 3 for Excel and VBA with the third segment, which is going to focus on optimization and curve fitting. And we're starting here with an example of a classical analytical function called the humps function. And it's shown here on the chart. And we have it set up to build a spreadsheet to produce the chart. What you can notice is that in the range 0 to 1, the function has two maxima, has one minimum here, and then actually the value at 0 is lower than this minimum. So let's take a look at this on the spreadsheet with the workbook that's called Humps Optimization Starter. So let's go over there now. Let's open this. There it is. And it just gives us a blank spreadsheet to work with and has an inset equation to remind us what the function is. So we'll come over and create columns for X and Y for our plot here. Do that quickly. And X is going to start at 0. And then we'll use editing fill series, columns, step value of 0.01, stop value of 1. And this creates a column of values for us. And then we can put in a single formula here based on this X value corresponding to what we have over here. So let's do that. Equals 1 divided by double parenthesis X, not X, B4 minus 0.3. Caret 2 plus 0.01, right parenthesis. Plus 1 by, again, 2 parentheses, B4 minus 0.9 squared plus 0.04, another right parenthesis, minus 6. So that gives us the value. Let me reduce decimal on that a bit. At 0, and if we double click the fill handle, we get all the values all the way down. And then if we select all of those values, tab, and we're back to the top, and do an insert charts, just lines, then this looks very much like the figure we showed you on the slide. So let's move that over to its own chart sheet. And there we have it, all right? And we can change things just a little bit here, but I'm not going to do extensive formatting. Let's make this like a 14 font in black, and this also. Grab this one and do right-click format, right-click format axis, down at the bottom here, number, and maybe places, so we'll put in 0, and we've got that. And then format this axis over here on the right and up at the top, and limit that axis to just 1, and spread out the curve, and maybe select the curve and make it black, a little more visible to us, and increase it a couple points, a little thicker. So there's our plot. We don't really need a chart title here, so I can delete that. And so there's our function, okay? So now what we're going to do is we're going to explore how we'll pick finding a maximum of this function. And to do that, I'm going to set up another separate pair of cells over here. You don't necessarily have to do this, but I'm going to do it this way. Let me just move this up to the top. Select cells. I'm just going to put labels X and Y here, and then right justify those. And I'm going to transfer those labels over onto the cells to the right as names. So this is now X and that is Y. And you can see that I have a macro to do that because it happened so quickly. Looking at our function, I'm going to pick an X value of 0.7, all right? Just to start with. And I'm going to build my formula again, be patient, equals 1 divided by, now X minus 0.3 right squared plus 0.01 right parenthesis plus 1 by X minus 0 squared plus 0.04, let's make sure I have that correct, minus 6, okay? So this gives me, I'll reduce it, does it, 12.38. And the first way we're going to explore this is using the solver. So I'm going to go to Data, Solver, move this a little bit to the right, and I'm going to ask for a maximum by changing cells X. And I'm going to click Solve. And let's see, it looks like it's come up with something, so it's given us a value right about 0.9 for a maximum. And let's look at our chart. And that's over here. So what it has done when we started with an initial estimate of 0.7 is it has provided us with automatically with the local maximum over the range, but not the global maximum, starting with a guess of 0.7. Let's go back and try a 0.5 instead. That places it over here, and let's see what it finds there. And the solver remembers, so we can pick it up and ask it to solve. Click OK, and now it gets 0.3, all right? And if we come back and look at the chart, 0.3 is this maximum here. So it's evident that the finding of the maximum using the solver is when you have multiple local maxima is sensitive to the initial guess. Now let's move back to 0.7 again, and we're going to make a change in the settings of the solver. So let's go to, we've got the method is the GRG nonlinear. GRG stands for Generalized Reduced Gradient, is the method. Click Options and click the GRG Nonlinear tab, and then we're going to say use multi-start, all right? And then we're going to add constraints. So the first constraint is going to be that X has to be less than 1. This is required, by the way. And the second constraint is that X has to be greater than or equal to 0. Click OK. And we now have two constraints sitting here. And we're starting at 0.7, so we'll ask for it to solve and click OK. And you'll note that it got the correct global maximum when we gave it the multi-start option, all right? So in the case of optimization, when you might have multiple maxima or multiple minima, then you might want to consider using the multi-start. And then again, if we would like to see about finding a minimum, it's not a very difficult thing to do if we just pick the current situation and ask the solver to find a minimum instead of a maximum and ask it to solve. It found 5.18 as a minimum, and that, it turns out, is here, all right? So it found the minimum, not this local minimum, but this one back here. So again, you have to be a little bit careful, and it's always good to try and understand the nature of the function that you are trying to maximize or minimize. And the other thing we note is that this method provides a dead solution, meaning that if anything should change, then you're going to have to run the solver again. So in a way, it's similar to using the solver or a goal-seek to find the solution of a nonlinear algebraic equation, where you get a dead solution and have to resolve it every time anything would change. So just as we did in a similar way that we did with nonlinear algebraic equations, we're going to consider an alternative here, which is finding a way to have a live solution, all right? A live solution for the minimum or the maximum on the spreadsheet, so it would, no matter what changes, it would always provide us with the correct value. So let's go back to the slides and get into that. This just reviews what we did with the solver, all right? Finding the local maximum from 0.7 and the true maximum from 0.5. And then it shows taking us through setting for multi-start and then it finding the true maximum from there. And so let's move on and talk about a method for finding, for setting up a live solution. And the method we're suggesting here is a famous and traditional one called the golden section search. It's certainly not the only one, and it's not quite the most efficient one, but it is so well known and so well used that we're going to deal with it here. So what we've done is we have shown an arbitrary curve here, and we're suggesting that we're going to try and find the minimum between bracketing initial values of A and B. So to do this with golden section search, what we do is we compute the golden ratio as square root of 5 minus 1 quantity over 2. And that happens to have a unique property, and that's described there. Golden ratio shows up in all kinds of different areas, such as architecture and nature, etc., as the limiting value of the Fibonacci sequence. And so what we're going to, this is a value of about 0.6. We're going to take the interval b minus a, and we're going to multiply it by about 0.6 or 0.62 and get a distance d. Then we're going to take an x1 value by measuring d from a, and an x2 value by measuring d back from b. And because of the nature of the 0.6 of the interval, these will overlap somewhat. And these give us the x2 and the x1. And having that in place, we're going to move on, and we're going to figure out how we go from here. And so if we're looking for a minimum, what we see here is that our f of x2, which is here, happens to be greater than the f of x1. So if we have a monotonic function with a single minimum, now we know that the interval to the left of x2 is no longer of interest in terms of containing the minimum. So as we go forward now, we're looking between x2 and b, so x2 becomes the next a, all right? Now, if this were the other way around, all right, and the f of x1 were greater than the f of x2, then the x1 would become the next b, and we'd be looking between a and b, all right? And every time we run this, the relative width of the interval that contains the minimum is reduced by that factor of golden ratio, which is about 0.62. So that's how the method is set up and worked. So what we're going to do now, keeping this in mind, is we're going to go back to the spreadsheet, and in the same way we set up bisection, we're going to set up the golden section search, all right? So let us come back to our spreadsheet, and I am going to put in a title here using solver, and I'm going to do a save as, and I'm going to call it humps optimization with solver. Save that. And then I'm going to close this file. And I'm going to open again the humps optimization starter. So I start with a blank sheet here. And now let me put in a subtitle using section search. Okay? Let me move this up over here just as a reminder. And I will come in now and put in some headings. The first is going to be iteration. Then I'm going to have A. And then I'm going to have my x2 value. I'm setting this up the way that it appears on the diagram. F of x2, x1, f of x1, and then the b value. Let me move this over a little more, and the d value, which is the width. So let me center those headings, and we're going to do the initialization row, all right? And up here, let me put in a label up here, GR, and I'm going to name the cell to the right GR, and I'm going to put in a formula to compute the golden ratio. Square root, sorry about that, square root of 5 minus 1, quantity divided by 2, and then there's your value of 0.618 approximately. Okay, so now let's start working on our table. We always start with iteration 1. We'll start here with initial estimate of 0.4 for A and B 0.8, all right? Then we need to know what the D value is, and the D value is equal to the golden ratio times the B value minus the A value quantity. And so there is our D value, and then x2 is equal to the current B value minus the D value, and x1 is equal to the A value plus the D value, all right? So you see the overlap in that the x1 is greater than the x2, just like our diagram. Now I need to build my function evaluations, keeping this guy over here in mind. So I'm getting good at this, I've got some practice now, equals 1 divided by double parenthesis this x2 minus 0.3 right parenthesis caret 2 plus 0.01 right parenthesis plus 1 divided by double parenthesis C4 again minus 0.9 right parenthesis caret 2 plus plus 0.04 minus 6. So this evaluates f of x2 with respect to this value, so I can just copy this over to this cell and it will now evaluate it with respect to x1. And we notice here we're finding a minimum, so the f of x1 is less than the f of x2. Might not be the case always, but it is in this case. So for the next round of the method, my a value will become this value, all right, tightening up the interval. So let's now put in the operational row, starting with equals up plus 1. And then we're going to create an if statement here, equals if, all right? And then we will say equals if f of x2 is greater than f of x1. If that's the case, then the new a value is equal to the x2 value. Otherwise, the a value doesn't change. So in this case, we've got our new value. Now, we then have to be careful how we do the b value, because that's going to be equals if, all right? So we're going to say equals if f of x1 is greater than f of x2, then this x1 value becomes our new b, otherwise we have the same old b. And that's what we have in this case. Now the rest of these formulas are operational, so I can just copy them down. Looks like something's not correct here, but let's check. All right, so let's just check what's going on here. This becomes, all right, that seems to be okay. This went 1. Then I should be able to take this operational row and run it as many intervals as I like. Now, one way of understanding that is to say, well, if I run it 20 iterations, the relative interval will be reduced by GR to that number, so it'll be 10 to the, it'll be 7 times 10 to the minus 5th, or about 1 in 10,000. If I run it 30 intervals, it's going to be less than 1 in a million. So maybe I'll run this 30 intervals. So I'll take this one here, starting at 5, and I'll drag copy down to row 34. That should be about 30 intervals. That's 1 extra. So let's get rid of that. And then what it says here is that our minimum occurs at 0.637, all right? And if I would like, I can just come back up here and say minimum, and then I can do a pointer formula down here to one of these values. They're all pretty much the same. Then I can say function value at the minimum, all right, is going to point down to the bottom, and that's going to be equal to this. So this has determined the minimum for us, and it is a live determination now. And if we take a look at our original curve, you will see that this has determined the minimum for us. And it has the advantage that it is a live calculation. And so if we had another equation, not this one, that had parameters in it that might change based on other cells on the spreadsheet, this scheme would always compute the minimum for us, okay? So let's review that on the slides, and then we're going to take one further step, just as we did when we worked with the bisection method. So back to the slides. So this is how we set up pretty much the initialization row, and I've provided you on the slide here exactly what are the formulas, just in case you need to check that. And then we moved on and we built the first operational row, and we show the formulas here, and the critical ones are the two if statements. And then we show the bottom here of the solution with the minimum at 0.637 with a value of 11.25. Okay? So now what we would like to do is come back to our spreadsheet, and we're going to consider another way of going about doing this. And that is, I'm going to set up cells for A and B, and the maximum number of iterations, and then we're going to find a minimum at a value, and we're going to have a value of the function there. So we're setting this up in a different way. Let me bring this to the right and take these three cells and transfer the labels as names. Again, put in the initial values here. We expect to use, like just with the same as our on the sheet solution, initial estimates of 0.4 and 0.8, and 30 for our maximum iterations. And then we're going to shift over to the Visual Basic Editor and show you how we have created functions to automate this scheme in VBA. So here is our function that's called min_gold. We'll sort of walk you through this. It very much reflects exactly the scheme that we implemented with our prototype on the spreadsheet. Starting with the function statement and the three arguments A, B, and the maximum iterations we're going to run. We have declared some variables. We'll come back to that. We compute the golden ratio, all right, value, and then we run a for next loop 30 times, whatever max it is equal to. And in there, we calculate the current value of D, which is golden ratio times the difference between B and A. And then one is A plus the D, the X2 is B minus the D. with the overlap, and this is the if statement that we implemented in on the spreadsheet. And if this is true, then x2 becomes the next day. Otherwise, in this case, we don't need another if statement. The x1 becomes the new b, and then we iterate 30 times. When we get to the end here, we're finished. We can take either the a or the b or the x1 or the x2. And it's not really necessary. They're so close together, but we can take the average of the two and return that. And then in order to be able to calculate the function values, we've established an adjacent function here based on our formula. And just note that as we put this together, as we've emphasized a number of times in VBA, you have to force spaces around the exponentiation or caret symbol, as you can see both here and here. So if we go back to our spreadsheet and say now we want equals min gold, A, B, and our max it value, this gives us our correct solution, just as we obtained from the spreadsheet scheme up here. And then if we want to, we can use VBA and say that the value of the function is just our function f evaluated for that correct value. So there you go. So what we've done here is very similar to what we did with the example with bisection, and that is that first we used the solver to find a minimum or maximum, and then second we developed the live solution using golden section search on the spreadsheet, more as a prototype than anything else, and then finally we elevated that into a VBA function which is very compact and hidden away from us when we're working on the spreadsheet. So that completes this example. So let me do a save as and call this humps optimization golden section or something like, well, it's not going to like that. We have to change this to a macro-enabled workbook because we have VBA code. Now it should like it. Okay. So there is that. Now we can, if we want, we can close that particular workbook out. And we're back to square one. So let's continue with our optimization theme here and consider an example where we're manipulating more than one variable to achieve an optimum, and we're also subject to constraints. And this, again, brings in the use of the solver. So back to our slides. So this is the VBA code, and it shows the example over on the right and the associated formulas. All right, and so we've gone over that. Now the next example we're going to use is what's called a grain bin design, and we've got a bin which is a cylindrical part on top of a conical part, and there would be an opening at the bottom here, but don't worry about that in this example. And variables we're interested in here is the radius here, be the same as the radius here, the height of the cylindrical part, the height of the conical part, and we're interested in this angle phi or phi here between the vertical, and you'll see how that comes in. So we have formulas that describe all of this. Fairly simple: volume of the cylinder, surface area of the cylinder. Not this does not include the top in this case, the volume of the conical part and the surface area of the conical part, and then a formula using the inverse tangent to determine the angle. And what we would like to do here as an objective is minimize the surface area or the material used to construct the bin, whatever it is, galvanized steel or whatever. And then we have constraints in that we want the overall bin size to be 10 cubic meter. And then we want the maximum angle here to be 20.4 degrees because this is an angle that relates to what's called the angle of repose of the solid material that's going to be flowing out of the bin. And if we make the angle greater and essentially have the sides shallower, then the granular material will hang up on the sides of the conical part and will not flow freely. So we put that in as a constraint that the angle can't be greater than 20.4 degrees. And I think that might be the angle of repose for granular corn. All right? So let's come over and see how we can set this up using the solver. And we'll come back to our spreadsheet. And we'll open a file from your collection of files, which is called grain bin. Here it is. So we've just entered calculations here, and let's review them here. First, our adjustable variables are the radius, the height of the cylinder, and the height of the conical part. And we have just put in nominal values of 1 meter here, which will certainly not be correct, but they're a starting point. And then we've come over and we've put in the formulas for that correspond to the volume of the cylindrical part, all right, the volume of the conical part, and then the total volume. And you can see how we're using cell names here. And that's supposed to be 10 meters cubed, and it's not. And then we've got the formula for the cylinder, all right, which is essentially circumference and 2 pi r times the height of the cylinder. And then the conical part, which is a little more complicated. And then the total surface area is the sum of those two. And our angle in radians using the atan function is given there. And then we've converted this using the degrees function over to degrees. And because of the nature of our initial guesses, this is 45. And you know that the angle must be less than or equal to 20.4, all right? So let us having looked at that, let us look at the solver, data, solver, all right? And nothing is set up yet, but let us say that our objective is surface area. We want to minimize that. And we want to minimize that by changing cells radius, HCYL, and HCON. And you can put in cell addresses there, but we've chosen to use the cell names. And then we're going to add our constraints. And our first constraint is that V has to be equal to 10 cubic meters, all right? And click add. And the second constraint is that PHID, the angle in degrees, all right, has to be less than or equal to, and I think our standard was 20.4. So we click OK. So we've now incorporated the constraints, the adjustable cells, and the objective, and the fact that we want a minimum, so we can try and see what we get here. And what we have is that the volume, and we can reduce our precision here a little bit to make it more reasonable. The volume is certainly 10 cubic meters. This gives us what the dimensions are, and we'll comment on that in a minute. And then this is the optimum solution of 20.9 square meters for our surface area. And you will notice that we have met that 20.4 degrees, even though it could be less than or equal to that. We are at that. The other thing that's curious about this solution is the fact that the cylindrical part is relatively tiny compared to the conical part. But that is the nature of the solution here, okay? So let's come back and look at our slides, and then we're going to move on to curve fitting. So this we went through. This shows the setup, and I've added a little color here, but it shows the setup and mentions that with our initial estimates that the volume specification is not met and the angle limit is violated. It's greater than our 20.4. Shows the formulas there, and here we show the setup of the solver with the constraints incorporated, and then the solution, and that has a small cylindrical part, and then we have our minimum area, and the constraints are satisfied. Okay? So let us move on, and we're going to consider curve fitting next. And we have an example here we're going to be working with, and that is a density of methanol water solutions at 20 degrees. We show a chart here, and you can see, if you gauge this, you can see that we have some curvature to the data, and what we would like is a polynomial that we can use that represents these data. So we're going to show a couple different ways to develop and come up with that polynomial. And to do that, let's open our starter spreadsheet for methanol water density. Okay, so back to here. I will just save this spreadsheet and call it grain bin finished. Close it out. And then we'll open methanol water density starter. Not much to this, it just essentially provides the data. So what we'll do here is we'll select these data and insert a chart. Just markers, all right? And then let's move our chart to a separate sheet, as we often do. And we'll do a little bit of work on it here. We'll increase this. This, all right? And then let's format this axis and have it just go out to 100, which is the limit of the data. And then let's format this axis and have the minimum be 750. And I think it automatically makes the top 1050, and that's okay. So now we've got that. We can add titles and such, but we won't do that. Let me just remove the chart title here. And let me increase the size and style of the markers. So we'll pick marker here, marker options, and I'll take the size up to 10. The fill, I won't have any fill. The border, I'll have a solid line that's black. Increase that just a little bit. Okay, so here are our data, all right? Now we want a polynomial fit to this, and the first quick way that we're going to develop this is using trend line. So to use trend line, I'm going to select the data, right click, and click add trend line, and it puts in a straight line, and we see the obvious problem there in that the low and high end are below the line and the middle part are above the line, so we have curvature here. So we're going to go to polynomial, and now we see that a second order polynomial fits the data better. Let me change a little bit the style of this, make it black and maybe a dashed line, and that may be up to about a 2 point. Less, okay, something like that. So that doesn't look too bad. Although if we look closely, we may see that the line is a little bit high here, the line may be a little bit low elsewhere, so we might do better, all right? So if we click that again, we might change the order of our polynomial, and for instance, go to third order, and it changes a little bit, fourth order, and fifth order. We got to be careful we don't pick an order that gets close to the number of our data, all right? But this sort of gives us an idea, and then we can say, well, what is the equation that describes this? And you have a couple options here. You can display r squared on the chart, and we don't consider r squared to be a very good measure of goodness of fit, so we won't do that, but we'll display the equation on the chart, and here it is. And there are a couple of concerns here. First, we can make it bigger so that we can see what it looks like. And this equation is a label. And if you take the values of the coefficients that are described here, I can guarantee you that if you compute with those, it will give you results that are way off, because you don't have the precision needed here to transfer these numbers. Now, one way we can work on that, we come back to text options and change category to scientific, and perhaps 4 decimal places scientific, and now we get much more precision in the model that's shown, and we actually can copy and transfer these coefficients over if we wish to use the model we have to predict the density, okay? So, and there are other concerns that we have here, in that we really don't have that great an idea about the statistics associated with this fit, other than r squared, which is pretty useless. So we're going to come back over now, and this is our fit using trend line, and then we're going to contrast this to a fit using the regression tool in the data analysis toolbox, okay? And so to do that, I'm going to create a series of labels here, 1, 2, 3, 4, and 5, all right? And let me center those. And then what we're going to do is we're going to create what we call an X matrix here by taking equals the methanol weight percent, and I'm putting in a single formula, so I'm going to hit the F4 key 3 times. That locks the A column, but not the row, to the power up here, which is in this case just one, and I'm going to hit the F4 key twice, which locks row 2, but lets the columns vary. And then I can come over, and these, of course, are going to be somewhat boring, up to the 5th power, and then down here to the 5th power. Now, I will mention that a concern that we have here that we can get by this time, but a concern that we have is that we've got very large numbers down in this corner of this matrix. And that can cause computational difficulties. And one way we get around that is by converting the 0 to 100 numbers to numbers of a much smaller scale, all right? Like 0 to 1, or one way to do it is to take the numbers and then subtract away the average and then divide by the standard deviation. But we won't do that here. So we have this, and now we are going to go to our data analysis toolbox, and we're going to pick the regression tool and click OK. And it wants to know the input Y range, and I'm going to take the density values, including the label at the top. For the input X range, I'm going to take this X matrix, including the labels at the top. Then I'm going to check labels here, that labels were used. It's going to put my regression results on a new worksheet. And I'm also going to ask for it to provide the residuals or the errors between the model and the data. I'm not going to ask for any of the other things here because we prefer to create those ourselves. So we're going to click OK. And this gives us the results of the regression calculation. Now we can work on this a little bit in order to format it a little better. Take out some information that's duplicated here. And this provides us with, for our 5th order model, it provides us with our multiple R and R squared. It provides us with adjusted R squared, and the model is an extremely good fit, so these aren't that informative. The standard error is an estimate of the error between the model and the predictions, and that's on the order of 0.1, which is very good, especially remembering that our values are in the range of 7 to 100 to 1,000. So our errors appear to be around 0.1. And there are analysis of variance results here, which are not meaningful at all because they evaluate the probability that our model doesn't do anything in representing the data. And that's, of course, ridiculous in this case. So let me delete those. And then it provides us with our model coefficients. But now we don't have to do any copying of values from a chart because these are stored at 15 to 16 significant figures, and we can use them directly. And then the other thing we can take a look at here, and I'm not going to get into the statistics too deeply here, is we can take a look at our p-values, perhaps represented as percents. And what we'd be interested in here is if we had any p-values which were greater than 1% or 5%, because they would identify a term in the model that might not belong there. But in this case, you can see that all these p-values are quite small, which indicate that the fifth order model is probably a valid model. It gives us that additional information rather than just trying it with trendline. And then finally down here, we've got our predicted values and our residuals. So coming back over to our chart, all right, this was our chart with trend line. So let me change this title to trend line. And then I'm going to move or copy the chart. I'm going to move it to the end of this worksheet and create a copy. So this is now called trend line 2, but I'm going to change that and call it a regression. And then I'm going to remove the trend line. Now we're back to square one. Come to my regression results and take the predicted values here and copy them. All right. Select my chart here and hit the Enter key. Right. Let's go back. Okay. And I pasted the values. It shows them as little orange markers. So let me select that and format that data series and say that I don't want markers at all, but I want a line instead. And there's my line. Take this back, maybe create dashes again. And this is my fifth order model for the data. And that is what we show as a result of carrying out the regression. And then another thing I can do immediately here is I can do what's called a residuals versus fits plot by selecting these and inserting a chart. And this particular chart, I can expand this axis a bit. And 750 to 1050 maybe. Did it get? It got 1050. And I'm not moving that, but essentially what I'm looking at here is, do the residuals show any systematic behavior? You can see that they're all roughly within that range of plus or minus 0.1, which was predicted by that standard error. And that really doesn't show anything systematic. And what that indicates is that our model is adequate and the overall standard error or variation shows that it is quite accurate and adequate. So we have a good model. And we have the coefficients of the model in full precision here, should we wish to use it to predict the density down the road. All right? So this takes you through a couple ways of going about fitting a polynomial to data. So let's come back to our slides. This shows the first thing with using the trend line and the fact that it really wasn't adequate, and then increasing, in this case, taking it up to third order, and it looks like a better fit, and then display the equation on the chart and change the style and precision of the coefficients, so they might be used for calculations elsewhere. And there's some notable errors that have been made by people, sort of embarrassing errors, where they have taken the initial equation that's displayed here and attempted to use that as a predictive equation, and it's way off, all right? And then we set up our X matrix with our calculation. Here it's shown with scientific, but that's neither here nor there. Set up the regression tool, choosing that, including the labels, and then came up with the regression results. And then I have translated the values here to show an algebraic form of the equation. You can see what it looks like. And then we had our chart of the results, okay? And then finally we looked at the residuals, and there wasn't any significant pattern there in our residuals versus fits or residuals versus predicted values chart, which is a standard type of chart to use. Okay, so we have two more examples that we're going to show in terms of curve fitting. The first one is, instead of polynomials, which are in terms of a single independent variable, in this case weight percent, we're going to show when we have multilinear regression, more than one independent variable. And when we have that, we're just putting down a little bit of background here, general background, because this will help us understand what's going on here. We have a model now for multilinear regression, which is linear in the parameters that we're fitting. That's the key part. But each parameter can involve a function of more than one independent variable. And so we can have, and it may just be an X and an X1 and an X2 and an X3, but it could be any formula that involves a set of independent variables. And this is what the form that's required for multilinear regression. And so what we can do is summarize the analysis of this by saying that we collect a number of measurement responses, here denoted by n, and then we compute what's called a realization matrix, which is all of these. The first one for the intercept, the function is 1, all of these functions evaluated at the corresponding values of the x's that yielded the y measurements. This gives us what's called the big X matrix. And then we have estimates of our parameters, not the true, but the estimates. And we have our data set, all right, which was used to compute this matrix. So we have n data for different values of our x variables. And then what we say is, given this setup, if we take x times beta here, that is our predictions of our measurements. So our errors are the measurements minus the predictions. And then what we want to do is we want to minimize the sum of the squares of the errors, also shown as the inner product of the error vector. We want to minimize that by adjusting our betas. Now, because of the linearity here, this problem can be solved via calculus, taking derivatives setting equal to 0, and we end up with the solving of the normal equations to find the values of b, which are our estimates of the parameters for our given set of data. And that you can actually describe this by solving this equation analytically X transpose X inverse X transpose Y, although when they program this, they actually just solve this set of equations, linear equations. And you'll notice that the size of these equations is the number of parameters, k, and not the number of data, n. All right? So what we're going to do here is we're going to show you, for an example, how we can use data analysis regression in order, the regression tool from the data analysis toolbox, to solve this kind of a problem. So here is the problem that we're taking a look at. And it is the density of salt solutions at different temperatures for different weight percents of salt, all the way up close to saturation. And so these are densities in grams per cubic centimeter, taken from Perry's handbook. And we're proposing a model here, which is called a response surface model, which allows for curvature. So it's got a linear term in weight percent, a linear term in temperature, a squared term, weight percent, a squared term in temperature, and an interaction or bilinear term in excuse me, in terms of weight times temperature. Now, let's go over to a starter spreadsheet here. Let me come back to my sheet 1 here. And let me do a save as for this. And let me call it methanol density water finished, and save that. And then I'm going to close that out. Regression starter. Okay. Now, this shows the initial table, and then in order to carry out our regression calculations, we need to stack these columns and create another column of temperatures. So we've taken the time to do that for you over on this spreadsheet. Let me expand that a little bit for us. So here we've stacked the values from the column, and we've indicated the format of the model that we're trying to fit here, all right? So we're going to put some labels over here according to the terms in our model, W and T, and I'll just put W2 for W squared, and T2 for T squared, and then WT, WT for the bilinear term, okay? So, and then what I want to do is just map these over. So I'm going to do a pointer formula to here. And then if I just drag that over, it then references temperature. Then I'll do a pointer formula to W again and square it. And drag that over so it's temperature squared. And then put pointer formulas for W times T, okay? And so that's the form of the model. Let me move that out of the way. And then I can take this and I can drag copy down, get my complete matrix here, all right? And what you remember from the X matrix in the slide that the first column was a 1, and with the data analysis regression tool, it puts in that one for you, so you don't need to specify it in the X matrix here. All right, so let's come back and go to data regression, and the Y range is that column, including the labels. I'm including the labels here because it's useful. And then the X range is that. I've got labels, residuals, etc. So I click OK. And here, once again, we have our regression output. And I think amongst your files, let's see if we can open this. File called regression format macro, and it's a separate file that contains a macro in VBA to automatically format the regression output. You can always go and take a look at that code. We won't do that now, but with this selected, if I do a Control-Shift-R, it automatically formats the regression output. It turns out the lower and upper 95% confidence limits are duplicated, so I can get rid of those. And it gives us our R-squared and adjusted R-squared and standard error. It gives us our coefficients. You'll notice the p-values are all very small. And then it gives us the predicted density and the residuals, okay? So we've got that. Now, in creating a plot here, one of the interesting plots is to take the predicted density column, and let me copy that back to sheet 2 and put it in here, all right? If I want, I can take this, transfer this format here to all of these numbers, so at least they look similar side by side. So you can see that that these numbers are slightly different, but they're somewhat close to each other. And before, like with polynomial fits, we plotted something against one independent variable. That's not that convenient here because we have two independent variables. So one useful plot is to just plot the predictions versus the data. If we had perfect agreement, this would be on a 45-degree line. So let's insert a chart with markers, and then let's move this its own chart and do a little bit of work on it. And so, as usual, make that axis more visible. Likewise. That precision to 1. Okay. And I could add labels, etc. I won't take time to do that here. Let me take this axis here, and we'll run at minimum from 1 to 1.25, okay? Here, and then we'll want the same here, 1 to 1.25. And here are our data. So let's show our data markers a little more visibly here. Solid line, which is black, and something like that. And then we can say, well, you know, that looks like very good agreement because it's 45-degree line. And if we wanted to, this would change if we start to add titles and everything. But if we wanted to at this point, we could use a drawing tool here. Draw a straight line from this corner up to this corner as best we can get it. And that is our 45-degree line. And then if I want, I can format the line to be black and maybe not quite so visible, or dashed or something like that. And so this gives us an idea of the agreement of our predictions. And for instance, if we saw this drifting off anywhere, it would indicate that our model is not particularly adequate. And if there were a lot of noise in the data, it would give us an idea of what kind of errors we have, all right? Now, the other thing, just as we did before, is we can do a residuals versus fits plot, all right? And then we can take this and perhaps again take this from 1 to 1.25 and look for any systematic behavior. And we see a couple low values down here. There may be this value up here, but generally there's no real systematic pattern, okay? So this gives you the idea of how you can go about doing that calculation for the using the data analysis regression tool. So let us come back to our first sheet here, and I'll just put over here using data analysis regression, and I'll do a save as, F12 key, data analysis regression. I'll just do analysis and save that. And then I'll close that out. I'll close this regression format spreadsheet with the macro for formatting that result. And then we'll open again the regression starter spreadsheet, and we'll go about this a little different way with live calculations on the spreadsheet, okay? So we're going to set up a similar X matrix here now, but we're going to have a column now for the intercept, and then we'll have W, T, W squared, T squared, and WT, all right? Just like we had before. So now we'll create our first row with 1 for the intercept coefficient and point to the W value here. Drag copy that to pick up the T value. Point again to the W value. and square it. Drag copy that over. Equals, point to the W value times the T value. This gives us our first row, and we need to be a little bit careful how we do this because we want 1 to be here also. So let's copy this first row down with duplicate 1s. First column, excuse me. That gives us a column of 1s. And then we can double click the fill handle to hang on that column and get the rest of them. And then what this essentially represents for the calculations is the X matrix. So let's take these numbers name X for these numbers, and while we're at it, we'll create a name for the density numbers, just the numbers, not the heading, as Y. Okay, so that gets us a start. And then what we now have created is this X matrix and the Y matrix. So we're working toward this formula down here. So we need to create X transpose X and X transpose X inverse. So let's move over here to the right. Put a little title here for X transpose X. Down 1. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This gives us a 6 by 6. So we'll put in a formula. All right, equals MMULT of transpose X times X. That gives us X transpose X. And we can name it XTX over here. Then we'll do another title XTX, whoops, XTXINV. Here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This gives us a 6 by 6 here. And this is going to be equals MINVERSE, minverse of X transpose X. So this gives us the inverse matrix. Let's name that XTXINV. All right. So this gives us that one set, and I don't want these here. So I'll come down, and now what we need is X transpose Y. All right. If we come back and look at our slide, we're forming this product over here. So 1, 2, 3, 4, 5. This is just a column vector, so it's equals MMULT of trend. Okay. So there we have those values, and let's again call this XTY. And then for our B coefficients, all right, the model coefficients, I'll just create a name B for that. This is going to be equals to MMULT of X transpose XINV and X transpose Y. And these are then our model coefficients. If you go back and look at the calculations we did with data analysis regression, I believe you'll find that these are equivalent, and these are our B coefficients, all right? So if we want to, we can come back over here and predicted density, all right? And let's select the full range here. And we'll put in our formula equals MMULT X times B. And these are then the predicted densities. If you come back to our slide, that's down here, all right? So there we have those. And then we can go about this exactly as we did before. If I want to slip in a column here, I could put in residuals, and that would be equal to the density minus the predicted, and carry that all the way down. And then I'm not going to go through all the formatting, but if I select these two columns, all right, and insert a chart with markers, that's our 45-degree chart, okay? So let's get rid of that. Or I can do my residuals versus fits chart, all right? What we had before, okay? So this is going through the calculations using the live matrix calculations on the spreadsheet. Again, it's our contrast between running something like data analysis regression and getting a bunch of results or dead numbers on a worksheet, or running a live calculation. And where this in particular can come into play, and I've seen it as such, is if you have a spreadsheet where data are being acquired from an experiment or from a process, and the data would change as samples with time, you can set up a regression that will respond to any changes on the spreadsheet and automatically adjust the model that is being fit, whereas you cannot do that using data analysis regression. So let me come back here and just put here using vector matrix calculations, and I'll do a save as regression, and I'll just put vector matrix on the end there. Okay, so let's close that file. And we'll pop back over to the slides and carry through with that. This is our example with the equation. And then we set up the X matrix without the column of ones and set up the analysis regression tool, received the results with the model, and then we did it alternately using the X matrix with the column of ones and the various X matrix calculations to come up with the model parameters, and saved that as our final result. And here are well-formatted plots of the agreement plot and the residuals versus fits plot, okay? So now we're moving on to the last example of this segment of the Bootcamp, right, 3. And this is nonlinear regression, which is even more general, because now we have a model for a response which is a nonlinear function of both our independent variables and our parameters. And we collect the data set as before. So with the data set, we can calculate function evaluations, all right, model predictions for this. We also have the actual experimental values, so we can subtract the model predictions away from those, given an estimate of our parameters, and get residuals. And then we use optimization to minimize the sum of the square of the residuals by adjusting our model parameters. Very, very general. So what we're going to do is look at a well-known example here, and that is fitting the Antoine equation to vapor pressure data. And we have a spreadsheet set up for you here, but these are the data, their vapor pressure of concentrated sulfuric acid at different temperatures from 35 Celsius to 290. And one thing to note here that we'll get to later is that the vapor pressure here is very low, and here it's 790. And actually the ratio of this to this is over 500,000. So there's a tremendous difference in the magnitude of these values and these values. But the Antoine model is a logarithmic model in terms of vapor pressure. And we've seen that before with a previous example for water steam data, but that's what it is. So now what we want to do is we want to fit A, B, and C, all right, given these data. So let's go over to our spreadsheet and open a file called Antoine Starter. And what you can see here is that we have our data, and it goes all the way down to the bottom, and they're set up in columns. So now what we're going to do is we're going to create a nonlinear regression calculation to determine the values of A, B, and C. One of the first things I'd like to do is just take the raw data, all right, and insert a chart with just markers. And you can see what we're dealing with here, where you have a very flat, tiny curve here and larger values here. Now, the problem with fitting a model to this is that when it comes to minimizing least squares, is that the model fit is going to care very much about fitting these values and not very much about fitting these down here because they are so small. So we can just move that chart over to its own sheet, come back, and we're going to work on this, so let me make it a little bit bigger for all of us to see. And we'll start by creating a column for log 10 vapor pressure, okay? So this is going to be equals log 10 of this value and all the way down, okay? Now, one thing to take a look, it starts from about -3 and goes down to about +3. So much easier magnitudes to deal with. And if we take the temperatures here, log values, and we insert a chart now of these, then you can see that it's much more reasonable in how it depicts the data on a scale of ±3, and that can be advantageous when we try to fit the data to the Antoine model. So let's move this over to its own sheet for now. Okay. And I think we may have, okay, we have created a separate chart here of the data where we used a logarithmic scale instead of computing the logarithmic data and plotting it. That's just there for you to look at. Okay. So let us move on, and over here in column G, I'm going to put in labels A and B, and I'll use CC because we can't use a name C, and right justify that, create cells with those names, A, B, and CC, and then put in some initial values which are typical for Antoine models. And you can look these up in tables or at the back of a book like the Felder and Rousseau text. And I'll put in about 2,000 here for B and 250 for C. Now what we're going to do is we're going to come over and compute log 10 vapor pressure. So that is going to be equals to A minus B divided by quantity Cc plus the current temperature in Celsius. And that value is way off, all right? It's not accurate at all, but let's just copy that down, all right? And now what we can do with that, if we like, is we can take those values and copy them onto our chart here. They're shown in red, and they're way out of bounds. Now, let's bring this, let's move this chart back to, I didn't want to move it there, move the chart back to the spreadsheet. Let me reduce its size a little bit here. Sorry. One thing I want to consider is how would I adjust my parameters in order to get the predicted values a little more in the ballpark of the real values, okay? How would I make those adjustments, okay? So what I can do here is I could start experimenting and saying, what happens if the 10 went to 8? Well, that's good. What about 6? Well, that's much closer. What if this went to 2,500? Then it's down. What if this came to 7? So I can do a little bit of work to get my model into the ballpark before I continue the calculation. So let's move this back to its own sheet and come back to our... And so what we're going to then do is we're going to have a column to compute the errors, which will be the data log vapor pressure minus the model log vapor pressure. And these will be all the errors. And then over here, I'm going to create a formula SUMSQ, sum of the squares of the errors, and this gives us an objective. So now, for nonlinear regression, what this says is that we would like to adjust all three of these to minimize that, which is the perfect scenario for the solver. So let's come to the solver and say that this is the value. We'd like to minimize this, and we'd like to minimize it by adjusting these three values here. And let's just see what happens. Okay, you see how small this is? It was 11 when we started, and now it's about 1/1000 for sum of squares. These two values are now pretty close to each other. If we go back to our chart 3, what we see is that our model values are virtually on top of our data, all right? So if I format that second data series and get rid of the markers, but add a line, and then maybe make it finer and dashed or something like that, then I can see how closely the model follows the actual experimental data. This really implies two different things. One is it implies that the model is a very good model, and it also implies that the experimental data were taken with a great deal of care and have very little random error associated with them. So let us save as this spreadsheet as our final example, and call it Antoine finished, and save it. And then I can close that out. Okay, and we'll go back to our slides and just review this.
I don't know, but I found these results on search.
And this shows that plot using log 10 scale, all right? And then it shows the log 10 of our model prediction way off, and then I adjusted it to make it closer. But then we computed the errors, and in here the errors are much greater because after my adjustment of the model parameters we had 11, and here we have 1,000 now. And then we set up to minimize sum square errors by changing these, and it gave us a very small sum square errors, and the curve coincides very closely with the data. And these represent the residuals versus the fits, and the model turns out to be a very good fit, and that's where we are left with nonlinear regression. So this completes the final screencast for Bootcamp 3, and we provide a reference here, and we note that we have been through fairly extensive examples about how to use Excel and VBA to solve typical problem scenarios in chemical engineering. And now we will move on to Bootcamp 4, where we will be seeing more in a capstone sense how to bring together all that we have learned in the first 3 boot camps to attack a more complicated modeling problem in the form of 2 different reactors. So this brings us to the end of Bootcamp